Hello everyone. Today I will be doing a breakdown analysis of the OSDI 2016 paper, Intermittent Computation Without Hardware Support or Programmer Intervention. It is a collaborated work done by Joel Vanderwood and Matthew Hicks. Improvements in the design and development of computing hardware has driven hardware size and cost to rapidly shrink as performance improves. Rapid changes drive us closer to the realization of smart dust, enabling applications where the cost and size of computation had previously been prohibitive. We are rapidly approaching a world where computers are not just your laptop or smartphone, but are integral parts of your clothing, home, or even groceries. While Moore's law drives the development of more powerful computers, batteries have not kept pace with the scale of computation. The smaller size and lower cost of microcontrollers enables new applications, but their ubiquitous adoption is limited by the form factor and expense of batteries. Batteries also reduce the ubiquity of devices in cases like remote sensors, in unreachable areas where batteries cannot be easily replaced. Batteryless devices, instead of getting energy from a power grid or a battery, harvest their energy from their environment as shown in this figure. The sources of this energy could be sunlight, radio waves, piezoelectric sources or thermoelectric sources, as such sources that we found in nature every day and are renewable in their scope. Unfortunately, while harvested energy represents an opportunity for system designers, it represents a challenge for software developers. The challenge comes from the nature of harvested energy. Energy harvesting provides insufficient power to perform long-running continuous computation. This results in frequent power losses, forcing a program to restart from the beginning. In order to tackle with this, researchers have come up with intermittent computing techniques. The intermittent nature of harvested energy dictates an intermittent execution model, which is shown in this figure. In intermittent computation, the program state is frequently saved to non-volatile memory, a process called checkpointing. In case of a power failure, the device state resets, and on re-availability of energy, the device recovers its state from the checkpoint in the non-volatile memory. This figure shows the trajectory of normal execution versus intermittent execution progress versus execution time. As you can see, intermittent execution takes more time than expected execution. However, expected execution will fail in the intermittently powered devices as it would not be able to complete long-running programs. So, now that we know what intermittent computation is and that we require checkpoints in order to ensure forward progress, what kind of a checkpointing policy do we have to choose? Checkpointing can be of two types. Just-in-time checkpointing, where checkpoint placement is decided based on the current remaining energy level by some kind of a comparator and ADC circuit. Uh, Consequently, this method requires additional hardware support not found on commercially available devices. This is shown on the left side. The other method is continuous checkpointing, where checkpoints are placed at either some periodic interval or by manually inserting uh, checkpoints by a programmer. In both cases, the programmer needs to administer the checkpoints to ensure correctness of checkpoint placement. This is shown on the right side. Now comes in ratchet, which is the focus of this paper we are analyzing today. It follows a continuous checkpointing approach. How it does not require any hardware support or programmer intervention. Instead, it leverages the compiler toolchain to automatically insert checkpoints between re-executable sections. As such, Ratchet aims to reduce the burden on the programmer without added hardware support, providing a ready-to-dispatch solution for existing low-power energy harvesting target devices. Now, what are the challenges in creating such a system? Under normal execution, overwriting a previously read memory location is inconsequential. However, on systems that roll back to a previous state for recovery due to potential issues such as power failures, overwriting a value that was previously read will cause a different value to be read when the code re-executes, as this is illustrated in this figure. The figure on the left shows normal execution and expected behavior of the program. The figure on the right shows program failure and then re-execution from a particular point in the program after right after a read. And as we can see, this leads to a memory violation. In order to prevent these potential inconsistency problems, Ratchet inserts a checkpoint between write and the read. This breaks the dependency, separating the read and the write in different idempotent sections. Note that this holds for a potentially infinite sequence of writes and reads. The sequence will be idempotent if there is a write before the first read. This approach of creating idempotent sections is shown on the right. As we can see, now the program fails execution after the write, which is happening in sequence after the read. However, this time we place our checkpoint between the read and the write, and as such, when program restarts execution from the checkpoint, there is no memory violation and the program state is still correct. So let's understand how Ratchet is implemented. Ratchet identifies idempotent sections and inserts checkpoints at two different stages of the toolchain. A front-end intermediate representation level pass detects idempotent sections breaks by tracking loads and stores to non-volatile memory that may alias. This top-level pass inserts checkpoint placeholders that are eventually passed to the backend where machine code is eventually emitted. Now, let's understand what happens in the backend. The backend replaces pop-in instructions with non-destructive reads and a checkpoint followed by an update to the stack pointer. It reduces redundancy by combining checkpoints and minimizes checkpoint state size based on the liveliness. Let's look at both of them in detail to understand more about Ratchet. The front end. It conservatively identifies write after reads. It consists of alias analysis, which helps identify writes outside the local frame. A checkpoint is only necessary on the function entry if there exists a write that may alias with an address outside of the function's local stack frame. Ratchet only inserts a checkpoint along a control flow path if that includes a store to non-local memory. After finding all the write after reads, the authors use a modified hitting set algorithm to insert the minimum number of checkpoints between the loads and stores. Uh, let's now understand what the backend does. Let's take the example of a system with interrupts. This scenario occurs when an interrupt fires after a pop instruction. In this case, The pop instruction will read from the stack and update the stack pointer. When the interrupt occurs, it will perform a push instruction to call save registers in order to preserve the state of the processor before the interrupt fired. However, the state saved by the interrupt is written to the stack addresses that were read by the initial pop. If the system re-executes the pop instruction, it will read a value from the interrupt handler and not the original value. This may lead to implicit writes after reads, and as such Ratchet considers all pop instructions as implicit write after reads. Since pop instructions can only be detected in the assembly, this will be solved in the backend by the Ratchet. To solve this, Ratchet breaks the pop instruction into its building blocks. A load instruction which reads from the stack, which is the memory read, followed by an update to the stack pointer, which is the memory write. Next, the backend also combines redundant checkpoints into one. Redundant checkpoints may be caused by optimizations, scheduling decisions, and register spills. Next, the backend relocates the inserted placeholders at the front end to minimize the number of checkpoints required by combining them and avoiding bisecting condition code diffuse chains. Finally, the backend minimizes checkpoint state by only checkpointing live in registers. Traditionally, compilers keep a list of live in and live out registers to determine which registers are needed in a basic block to perform some computation and which ones are unused and can be reallocated to reduce register spilling. This information is available to the compiler after the registers have been allocated. Ratchet is interested in which registers are livened to a checkpoint because they denote the volatile memory needed to be saved to correctly restart from a given location in a program. Now, let's understand some of the optimizations that Ratchet does in more detail. These will involve some tags which we will keep on seeing in the evaluation section. As such, we should understand what these tags mean. The first tag is just Ratchet, which represents the unoptimized version of Ratchet, which conservatively adds checkpoints between all writes after reads. Ratchet FE represents Ratchet optimized for function entries. As we saw earlier, a checkpoint is only necessary on function entry if there exists a write that may alias with an address outside of the function's local stack frame. Ratchet FE plus RD adds another layer of optimization by removing duplicate checkpoints. Ratchet FE plus RD plus LR is the most optimized version of Ratchet, which also minimizes the checkpoint state by only checkpointing the live-in registers as we discussed previously. For evaluation purposes, the benchmarks are evaluated while being compared to the ideal case of a single checkpoint in the entire program, even though such an ideal case may not be realistic in ensuring forward progress. We need such a lower bound as it assumes perfect intra-procedural alias analysis and zero idempotence violations. Now let's understand the evaluation setup. The compiler implementation is built on top of the LLVM structure. For energy harvesting purposes, a cycle-accurate ARM v6m energy harvesting simulator is used. An energy harvesting simulator is required because of the difficulties associated with developing and debugging intermittently powered devices. Using a cycle-accurate energy harvesting simulator facilitates simulation of failures with a probability distribution that can model the true frequency and effects of power failures experienced by devices in real world. In order to provide a comparison against other checkpointing solutions for energy harvesting devices, uh, the paper evaluates ratchet on benchmarks common to these approaches, namely RSA, CRC, and FFT. These are all part of the MI bench repo. For a complete analysis, several benchmarks from the MI bench repo are ported, which includes a set of embedded system benchmarks categorized by runtime behavior. In order to ensure that each section of the code that runs on the device is idempotent, all the libraries needed by the benchmarks also need to be instrumented. Now, this figure shows the runtime overhead of different checkpointing versions of ratchet on the baseline of no ratchet across different benchmarks. As you can see, 6 out of 8 benchmarks fail to complete execution without ratchet. Overhead dramatically varies between benchmarks. This shows that performance of ratchet is highly program dependent. The average runtime overhead of ratchet is 58.9% for the most optimized version. This is 20% of an improvement over the unoptimized version of ratchet. This figure shows the average number of cycles per idempotent section break. Programs with shorter idempotent sections have higher overheads. This is because shorter sections mean more frequently inserted checkpoints. This figure shows the fraction of runtime overhead due to re-execution for a range of average power on times. While short idempotent sections tend to cause higher overall overhead due to checkpointing, uh, since checkpoint overhead dominates the total overhead, this figure combined with the previous results shows that benchmarks with shorter idempotent sections have lower re-execution costs. This is reasonable considering that a failure halfway through an idempotent section requires the program to re-execute from the last checkpoint. The more cycles since the last checkpoint, the higher the re-execution overhead. Finally, this paper also benchmarks ratchet across LLVM optimization levels. This figure shows the performance of benchmarks compiled with ratchet at different optimization levels relative to uninstrumented benchmarks compiled at the O0 optimization level, which is the no optimization level. In general, traditional compiler optimizations improve the performance of ratchet. In some cases, aggressive optimizations result in higher perceived overheads. This suggests that breaking the program into idempotent sections can not only reduce the efficiency of optimizations, but also cause them to be detrimental, as we can see in the case of Dijkstra. In conclusion, Ratchet is a compiler that automatically enables the correct execution of long-running applications on devices that run on harvested energy without any added hardware support. Ratchet leverages the notion of idempotence to decompose programs into a series of checkpoint-connected re-executable sections. Ratchet stretches program execution across random frequent power cycles for a wide range of programs at a cost of less than 60% total runtime overhead compared to other checkpointing schemes which require hardware support or programmer intervention. The paper also suggests with more engineering, it is possible to reduce runtime overheads to around 20%. As such, Ratchet offloads the burden of checkpointing decision on the compiler, opening the door for non-expert programmers to code energy harvesting devices. Thank you.